And well, yeah. So it was mostly about safety, and that the kind of safety that I talk about is probably not on the level that people are usually familiar with, in terms of we are guaranteeing safety on like a approvable level. So for example, MPC, you should say, oh, if we have a perfect model, it's usually safe because we ensure that every time step we don't hit anything. However, like in MPC, you still have the sampling issue where you make sure the car is safe at each time step.
Right.
However, you don't say anything about what happens in the middle. For example, if your DT is 0.1, then what happens during that 0.1 second? You can only say something about you can say something if you have like some speed bound or like some discretization fineness, and the finer you go, the more compute you get, and eventually it becomes not so elegant, let me say. So that's the setup. So let me go slightly into what I did and the philosophy basically in Rome lab, who is led by Professor Ram Vasudevan. I don't know if you guys, I don't know how many of you went to the talk a few weeks ago. No?
I think it was, yeah.
You were there.
No.
No. Okay. So, okay. So, the philosophy is motion planning usually don't consider tracking error a lot, and we well, I mean, in a drone world, we usually plan polynomials and assume we have some some good trajectories tracking that polynomial, some good controller tracking that polynomial, and however, sometimes some maneuvers are very hard to control, and they will introduce a lot of uncertainties on where your future position is. So we want to formalize a way of saying, hey, if we have very tight space constraint, then we don't want to take these hard to take maneuvers. So the solution that Ram come up with, which I extended extensively upon, is called reachability-based trajectory design, that chooses a trajectory based on how difficult the trajectory is and how much space there is, using our optimization, guaranteeing safety. So, yeah.
Okay. So when you say based on how, tight space.
Yeah. So, so of course the lab has done a bunch of stuff, which so some of them I contributed to, some of them not, and we have applied it on a lot of systems where the top left is like a small golf cart, and then top right the drone, bottom left manipulator, and then also walking robots. So it definitely works. And the basic idea is that first we parameterize the trajectory. So it's a very common technique where we say, okay, we're not going to take any combinations of control in the future 2 seconds, for example. We're just gonna consider the ones that are in our control parameter space, and this way we have a limited number of. We still have an infinite number of things we consider. For example, the x-axis may be the desired longitudinal velocity, and the y-axis may be the desired lateral position. So if we have some initial condition, we can just have a smooth polynomial connecting these 2 points and achieving a lot of different controls that way. However, of course, it's going to be somewhat limiting because you don't take different U input every time step, like you do in the optimization or MPC case. So that's the limitation, but it achieves, it helps us to say more about safety. So after we parameterize the trajectories in a way we like, we compute the offline reachable set, and then we compute it in a way that it is sliceable, which means we can take a specific point in the parameter space, like the green point, and then just shrink the offline computed reachable set really quickly online, so that we can do a receding horizon fashion for making this to plan forward step by step, basically. And as you can see, the obstacles are basically inside the trajectory parameter space, but in terms of optimization, we basically have run a constraint optimization ensuring, okay, and the decision variable are the trajectory parameters. So it's a low dimensional space, not as high as maybe MPC, which maybe 100 time steps in the future and 100 decision variables. Here is just 2 decision variables for the future, let's say 2 or 5 seconds, something like that. Okay, so now we know how it approximately works. Let me talk about what is the representation we use for the reachable set. Here we use an object called zonotopes, which looks like this. And let me just quickly draw this. This is basically the center of the zonotope, and you guys can see, yeah. And this is a zonotope in 2D. And when you add this generator 1, it becomes a line that looks like that. And when you add generator 2, it becomes a parallelogram that looks like this. And when you add generator 3, it becomes a hexagon that looks like the thing out there. So zonotopes are a good object to consider, because if you do polytope and do linear propagation of it and then try to bound the outside again, then the dimension gets the number of half planes you need to represent the polytope grows very quickly. But zonotopes, as this guy showed, who is actually was a Penn guy many years ago, it's very the number of generators, we say, grows, I think, linearly. I'm not too sure, but it grows reasonably with propagation for many steps forward. So why is this good? First of all, I mean, of course, to ensure safety, we need to outer approximate our dynamics. So that can be done here. And the second thing is, we don't have holes in between sampling times. For example, this is a zonotope at time equals 0. This is a zonotope at time equals 1. And this is a zonotope at time equals 2. Our reachable set looks like this. Basically, the reachable set from 0 to 1 looks like this, and the reachable set from 1 to 2 looks like this. So there are no holes in between time steps. But the problem with this approach that it can be generated sort of slowly, not as fast as we'd like. So you can't say, oh, let me generate this online and say it's safe. So basically, we have to resort to what I said earlier, which is computing things offline and then applying them online. So let me clear. This is an example of converting a polynomial reference trajectory into a zonotope representation. So here, the reference is basically a function of the reference, these lines are generated by k, which is the control parameter, and t in terms of time. So the the zonotope reachability thing basically takes in this ODE and propagate it forward. So these are basically explicit evaluation of the polynomial. But on the other hand, here is the zonotope generation of it. And the blue ones is the blue one together is the not sliced one, meaning as I was saying earlier, we generate something offline and try to slice it online really quickly. So the black one here is sliced one, which we say, okay, maybe k equals for example, if the k is what's the lateral displacement, k equals -2, then it becomes this black one here. As you can see, we do get some conservatism. As you can see on the black line on the left, it's very thin. On the black line on the right, it's sort of huge. But we do gain the benefits we talked about earlier. Any questions?
When you say sliced, means that for each of these light maneuver, you pre-compute the reachability, you propagate the dynamics, and then you aggregate them into the blue region, or
so
the blue region is pre-computed in one shot.
The blue region is pre-computed in one shot, and the black region is an operation that's really quick to get from the blue thing. We never do this explicitly. This is an example of evaluating polynomial, like integrating the ODE, like from 0 to t equals 5, for example.
So in real time, you have a lookup table kind of, and then you just index that lookup table.
Yeah. So these are saved as basically polytopes over time, and well, zonotopes over time. And when you have a parameter, it's a linear, it's a matrix multiplication, and you'll get basically if you have a C and G1, G2, these are the generators that I was talking about earlier. And when you slice it, basically you say, okay, this G is gone, and we replace it with the K value that we select. And that will be, if you plot it, it will become the black thing. Yeah.
Not even related. Not related. Is not related. It's just not the same thing. This is all a representation. Talk about reachability. This is about reachability.
Right. So like these lines you see depends on the dynamics. But I think
it does depend on the dynamics. Generating the speed trajectory is not doing any reachability. Oh, this is doing reachability.
Okay, so previously I talked about like zonotope reachability for linear systems, but there's a group in TUM, Matthias Ansaf, who worked on extending this to nonlinear systems, so we can have more representations for our reference trajectories. Yeah, so yeah, also slicing extensions. So, but the problem is this is still not good enough. Like generating these reference trajectories, generating reachable set for the full dynamics for example, if you have a bicycle dynamics and then you parameterize the steering angle from time equals 0 to somewhere at 2 seconds steering angle, like doing this, for example. If you do that for the full dynamics, still not good enough, meaning it will expand like crazy. So for example, here it's a polynomial, so it doesn't expand too crazy, but if you do the steering angle parameterization, it probably expands like this, which is pretty unusable.
What are you parameterizing for here?
Here is parameterizing. Actually, I have a slide coming up for that. If you just hold on for a second. So instead, what we do is we split the reachable set into 2 parts. One is the sliced planning reachable set, which is the black region that we talked about earlier. And another region is the arrow reachable set, which means how much difference is there between our real vehicle experiment, for example, and our black reference lines. So if we add these together, we will get the actual reachable set for the car. Meaning during experiment, we do, like, if this is the experiment trajectory and this is the reference trajectory, which is the black line you guys saw earlier. We take that difference over time, which we can attribute to, oh, this arrow comes from time equals 0.1 to 0.2. This arrow comes from arrow time 0.2 to 0.3. And we can make this arrow reachable set also a zonotope series. As a result, we can say, okay, the planning thing plus our arrow thing, which is the difference between the actual model and our planning model, would be where our car will be in the future.
So, before you said you have to hold the control input constant. Is that just between time steps?
You have to, so for this control parameter space, a point here, you have to hold something constant, but the something constant may be like, so for example, if you want to hold, like, say, okay, I want my car to go like this, which is AT squared, let's say. You have to hold this A constant. But that doesn't mean your trajectory is, or your reference is constant. It still evolves as with respect to T.
The only question I asked is because here, so the slice planning reach set, this is conditional on the point we pick in our control operating space.
Yes, control parameter set.
So when we calculate the slice planning reach set,
yes,
over this trajectory here that was pictured, there's a series of control inputs, right? You have to go left then right. Right, so like if you're the black car and you're trying to overtake the white car in front,
yes,
you need to accelerate, you need to turn left, then you need to renormalize your heading.
Yeah.
Right?
Yeah.
So
yeah, so in this case, you can think about, like, let's parameterize this with like a arctangent curve or something for the steering input. It still works, and maybe the magnitude is
what we call.
Yeah.
So we only have to hold one dimension of the control parameter space constraint.
I mean,
so like it can be some surface like that, right? Where, so like if your control parameter space has like 3 dimensions,
yes,
you know, you're trying to pick something on this control parameter space.
Yes,
you can just pick a rod, right? You can say, okay, I'm holding acceleration at 0.3, and everything else I'm changing. I can change along this rod. I can pick anything I want along this rod. I can change my steering angle, but so long as my acceleration is constant, it doesn't matter. I'm not understanding
Okay.
This part about what we have to do. So do we have to pick an operating point and leave that operating point for the entirety of the rollout?
Yes.
Okay.
But also it depends on your replan speed, right? Like we say, okay, if you pick a point,
yeah,
and let it run for this reachable set, which may be generated for 8 seconds.
Yeah.
It will be going, it will look like this for the future 8 seconds. But when you get to maybe 1 second forward, you say, okay, let me generate something else. So, so it will be able to do something else more frequently than the whole trajectory parameter space. We just ensure the safety for 8 seconds, which means if we don't do anything else, we keep our current operation.
Yeah, you're guaranteed.
We're guaranteed.
Safe option.
Yes.
Through the whole.
Yes.
Wait. This may actually make everything make sense for me. So the control parameter space is not actually. It is parameterization of control trajectories over the full horizon, planning horizon.
Yes.
It's not actually I'm picking this acceleration and this steering. It's I'm gonna pick this polynomial and this polynomial.
Yeah. So f of t and k. Right? K is the parameter. Yeah.
Oh, and to make sure the zonal scopes in the workspace or in the configuration?
They're in a full state space.
Okay.
Yeah.
But to compute the xenotopes, don't you need to map to the actual inputs?
Yes,
you have the polynomials, but to compute the reachability, you need the like acceleration and steering or something.
The reachable set is computed, so this part is computed for the polynomial, right?
For the polynomial.
So it doesn't have a factor of the vehicle dynamics in there.
Okay.
The vehicle dynamics come from this error, right? Which describes the difference between the actual car dynamics and the planning dynamics.
So if you go back to one of the slides that you had the dotted line, yeah, this one. So on the left, for example,
these are
5 points in the control parameter space, for example.
Yes, these are basically
and then
K choose one of the 5 points.
Yeah, and then on the right, how do you convert these points into the zonotypes?
Basically, you compute zonotype of t from 0 to 10, and then k from -2 to 2, all in one go.
So, like, for example, on the left is what the Fs would look like for like discrete set of k.
Yes.
And then on the right is like a continuous set of k.
Yes.
But that doesn't consider the dynamic.
No.
Okay. Oh, okay. I see.
Yeah.
What's the model you use here?
The car model. Here is not. No plot here is generated by a car model, right? But in the simulator, we use somewhat extended kinematic model because I'm going to say more. It's just the first work here is like that, because the main goal of this work is to do safe reinforcement learning, which I haven't talked about because I'm just going from a more basic, more core algorithm to applications.
How do you ensure that plus the ERS it's still reachable?
Because it's actually
so the ERS is generated by doing a lot of experiments, right? Like, oh, this is the EXP, this is our reference, and this is another EXP, another EXP, this is another reference. So
the EXP is corresponding to the reference.
Yes.
Okay.
The EXP is your experience of following that reference.
I thought you generate a bunch of EXP and you use
no
all of them.
Yeah, then it would have huge errors. We want them to correspond to each other. Yeah.
Then how do you do this experiment? That's a lot of things.
Yes, it's a sampling based method which makes all the guarantee go out of the window, right? Mm-hmm. So what happens is we have some notion of where would largest tracking error occur. For example, when you have the largest control parameter, for example, when you try to most aggressively change your desired lateral position, for example. So, okay, so that's basically the method. And now I'm gonna, okay. Oh, yeah, one more catch, or one more thing that makes it a lot less conservative is that for a region of the control parameter space, we generate its own sliceable reacher set, which can be sliced, and its own arrow reachable set, so that for each section, we have a different set of things. That doesn't do that doesn't remove any guarantees, but allows each section to be more local, more suited for this section of control parameters. So yeah, it does. We don't need to save a lot more things that way.
How do you go from observations of obstacles in the environment to
Things in the in the workspace of zonotopes and try to compare zonotopes and make sure they don't intersect? That I have some slides for, which I did not put in because I feel like it's a lot of details, but let me quickly describe. Basically, we have a zonotope Z1, which represent our car, and Z2, which represent the obstacles. And the crazy thing about this is the Z2 is represented by the obstacles, and it has, let's say, 2 generators. And if you just put these generators on top of Z1, which the first one would make you look like this, the second one would make you look like this. Sorry, I don't exactly know how it would look, but something that looks like this. So that operation is very quick because it's just, you have C1, G1, 1, G1, 2, which is your Z1, right?
mm-hmm.
And Z2 is C2, G21, G22. And you basically just say, okay, I'm going to move these ones here. Move these generators to the other generator.
Mm-hmm.
And then it's still in center generator representation. Now you make it to become half space representation, which is the most time consuming part, basically, to make all of these half space planes, hyperplanes. Yes, hyperplanes. And then you just check if the second center, the center is inside this hyperplane or not. And that's a very fast operation. Okay. So, yeah, this is just example where we have 4 parameters, actually. 2 of them are initial condition parameters, which we will slice according to the initial condition. And 2 of them are desired, which we can choose online. And it's on a straight highway, so the heading is absolute, like the heading is with respect to the, well, Fernet frame, let's say. So extensions basically, or the things I did is, because we can have this modeling based approach to safety, and it makes a high dimensional problem into a pretty low dimensional problem, we can use that for safe reinforcement learning, because reinforcement learning is sort of good when you consider, oh, we have Atari with 4 inputs or something. So now we just have a game that have only 2 inputs, basically, if you consider the two parameters that you can choose online, in my previous example. So that allows, one significant thing is that allows reinforcement learning in the real world without any training in the simulator. Basically, you can ensure safety, but the game that reinforcement learning is playing is a much easier game that never hits any obstacles. So, this is not a real world experiment. This is in the simulator, but the yellow and the black lines are the things proposed by a reinforcement learning agent. And the black line is the RT, we call it RTS, basically safeguard. The safeguard corrected parameters, polynomial reference lines. And you can see like on the top, it always ensures safety and even breaks to a stop when there's no safe parameters available. So one thing I forgot to mention is at the end of each planned trajectory, we have a fail-safe trajectory at the end that takes the car to a stop. So it's consistently feasible, as other receding horizon methods do. And on the bottom, you see like a naively trained or a baseline where it's only reinforcement learning based, and it gets to the goal 90% of the time, but crashes the other 10% of the time because it doesn't have this sense of safety. So, and on the right, you see how the correction mechanism works. Basically, if you have a parameter chosen by RL, and it will choose, and it will sample the parameter space and choose the closest one that's safe. And this is a reachable set for the green point that's drawn here. And we also do something.
I have a,
Yeah.
so for example, here, what do you know why is it trying to always drive to the left on the top one? It seems like it's always trying to drive to the left.
Huh, interesting.
Even in the lower one, you see like if there's no obstacle, it seems to tend to drive left.
I don't know. I mean,
I'm just friendly.
I mean, it's a
It doesn't have
DDPG.
fires.
It's a DDPG algorithm with like a few layers and a few tens of nodes per layer. So it's not gonna do anything crazy. But I mean, to its merit, we do see that like so we also compared this to RTD, which is optimization based. Basically, you have a waypoint saying, hey, this is our for example, if this lane has the obstacle that's the furthest, we say, okay, that's the lane you should target towards. However, in that case, there are some cases where the car will just sit behind it and get stuck because all reachable set intersect with the obstacle, right? So it won't go anywhere. But in the reinforcement learning case, we do find that these stuck behavior are less frequent. So the RTD gets to about 95% of the goal, whereas this RTS based on reinforcement learning gets to 100%.
Can you say something more like the existence of the fail-safe trajectory? Like, because this is like always ensuring that you have like this safe solution. So how it works, like it's a common assumption. I ensure you always have this option.
You have this the slowdown.
Yeah.
The fail-safe trajectory, yeah.
Yeah, like the existence of it, like.
Yeah, so the fail-safe trajectory in this pretty slow car, like 3-4 meter per second case, is pretty obvious, where all the obstacles are static obstacles that stay in place. But I did apply this to a Ford vehicle, which is the founder of the, well, the founding agency of the lab at the moment. So we do apply this there, and these fail-safe to stop the car from 70 miles an hour to 0 is not great, right? So I mean, I want to say, because we need, so you solve the problems you can, right? Like, because we need this safety guarantees. So we have to assume that such a fail-safe trajectory exists.
Can you do that if like the other is moving? Because it will depend on like. the
Yes,
future
yes,
behavior.
yes. So what we can say is, if we have perfect prediction of the other guys, then we are not actively hitting someone, meaning we're not at fault. And that's all you can say about the sense of safety, is you're not at fault when someone is trying to hit you. But I do want to like talk about, actually, what time is it? I don't want to talk about the Ford case, which is more practical, and I think it should solve some of the questions you have about this. But before that, we also I also want to show, this is the similar thing basically for a quad rotor, and it's the reinforcement learning just sort of learned a stupid trajectory to just always go forward and upward a little bit, because that seems to be the best. But the fail-safe, the RTS is just good because it will avoid things. So
The difficulty in extending this to future or to other systems is finding the control parameters. That's the hard part, right? Finding a good control parameter space for your.
find a control parameter space that's low dimensional enough for reachable set computation,
Yeah.
and high dimensional enough for doing interesting maneuvers.
Yeah. So I mean, like, honestly, cubic splines are good enough.
Yeah.
So my question in this case is, who's driving in this case, like?
RL.
Because, yes.
Yes.
Sure, but
Yes.
most of the time it's being corrected.
Yes.
So who's driving?
Yes. So yes. So it's so I also train a RL agent that doesn't use this RTS, right? It just stays in the what's that called? In the starting location, and don't move to the goal, because it's so far away, and there's no way it's gonna success and gain any positively reinforced reward. So
how have you tried just one command, just go forward and just use the RTS to correct it? Does it reach the goal?
it probably will 50-60% of the time. Yeah.
So you need you don't quite need an RL, right? You need some kind of simple.
Honestly, you could random
Heuristic.
sample points because the only collision you need to break properly would be if you're going straight forward and there's an obstacle straight forward, and the RT
Yes.
controller will just make you stop, right?
Yeah, it will just stop and you keep going forward. So it needs some sort of perturbation on the lateral direction.
Then you're good.
If your horizon is long enough, then we don't have it.
Yeah, speaking
Then
of
just
long
go
enough, I think
Just push it forward and it will
Yeah.
reach to the.
But the further you push the horizon, the bigger the like the
Yes.
reachability set explodes, right?
Yes.
So like, the more you increase it, the bigger it gets. And if you increase your horizon too far, then your reachability set gets so big that you don't want to move it out.
yes. That's correct.
You know, well, I mean, isn't not moving a good thing if you're going to split, right?
I mean, then you're not going.
Okay, cool. Let me so basically this is what I talk about RTS, which planning reachable set is sliceable envelopes. Error reachable set is samples of difference between planning model and the simulator. And high level planner is RL. The bottom ones don't really matter. And at Ford, we want to make things fast, right? Like we like to planning at 20 hertz, for example. And the high level planner, actually, they are powered by some RL algorithms. I'm not gonna say any details, but It's interesting. And however, the zonotope conservatism comes from like that you see in the black line to the black zonotopes is too much for industrial applications. Therefore, we try to evaluate polynomials online quickly. Of course, all the guarantees are not out of the window, but it's okay because we just need it to work well. So, and a good thing about this real world experiment is that we can actually do experiments of different perturbation, different actuation levels, and say, okay, well, what is the difference between our planning model and the experiment?
Oh, so you guys have a Ford.
I actually interned at Ford for 7 months to do this.
I'm wondering, why does it take 1.5 seconds?
Why does each so you want your replan speed to be faster than your trajectory, right?
Yeah.
Your trajectory may be 1.5 second long,
Yeah.
and your replan may take like 0.5 seconds. So first of all, everything is implemented in MATLAB, so it's not a particularly fast language. Compared to C++, I don't know. Yeah.
So I'm just saying, I don't care like if it's fast, the absolute speed. I'm just saying that what's taking the most majority part of it.
Yeah. So the majority comes from, so the things that needs to be done is like actually I don't have anything like an algorithm. The things that needs to be done is like, oh, you take whichever your initial state is in, slice your zonotopes with respect to the initial state, and then try to, and because you have parameter space, split it into regions, right? And you're like, okay, let's optimize, or let's say, where is the RL picking? And let's see if in the RL region, there is a available parameter that's safe. If not, we move on to another region, and then if not, we move on to another region. So that sort of the splitting of the parameter space is what takes most time, because you need to plan basically inside each region. If we have a tool that's good enough to generate the whole trajectory space, then we can do this very fast, probably under 0.1 second.
So how do you split your parameter space then? How do you do it then?
Uniformly, and grid, yes, but I think there are better ways to do it, which we haven't done. Because the tracking error is, let's say, oh, if your maneuver is very smooth, maybe the whole middle 80% of the trajectory should be in one region. Yeah, because the error won't be that huge. Yeah. I'm liking this iPad presentation. I haven't done any iPad presentations.
Yeah.
So this is the experiment of a real car, which we took into a ROS bag and converted it to our MATLAB visualization. There are 3 lanes. This white and that dashed line is dashed line, like solid line is solid line, and the car in front of us actually is riding in between 2 lanes. So it would be sort of hard for the traditional algorithms to avoid these. If you don't know like how much it's in your lane, do you consider it in that lane or in our lane? So, and at the same time, it will try to brake really hard. The car in front will try to brake really hard. We were sitting in the car very nervous and to see if our car can avoid the car in front of us that's coming.
Real car.
Real car, yeah.
Oh, so if it messed up, you get in a crash.
Yes, but and my boss sits in the driver's seat. I sit in the passenger seat holding a laptop, and he is always asking me, hey, is it gonna work? And then every time he's like, that's so bad, and he just takes over manually. But eventually it worked. So the yellow is when it's actually doing something, and it will snap to a grid if it finds another lane center that's safe.
I see.
And there are 3 trajectory parameter in this work, which is different from the RL work. It's the maneuver time, the amount of lateral change, and also the acceleration, a constant acceleration during the maneuver.
So is this
And
deployed on?
this replans at 20 hertz. So there are some problems associated with that, but I'll talk about that later. Any questions about this?
Is this deployed on real cars?
I mean, on the prototype, yes.
No, I mean like production.
No. It probably takes a few more years. And I don't know if it's gonna go on.
The green is your planning horizon, right?
Yeah, the length is the planning horizon. This is 8 seconds or 10 seconds. I forgot.
It seems like it's doing the maneuver like very late stage. Why is that?
Because you have predictions of the other cars going at constant speed. So, like, if they're at the same speed, then they're gonna move forward, then it's okay, right?
Okay, so the car braked.
Yeah, the car braked, and we still assume it's constant speed, but a little slower.
There are really simple trajectory prediction models, CTRA, CTRV. They're using CTRV, constant turn rate and velocity, which is like really simple to compute and pretty good. So when they slow down, you consistently update your trajectory, your predicted trajectory for that other agent updates at every climbing step. And so once that car slows down here, you can see that collision is like effectively avoided, right?
Yeah, and
I'm wondering,
yeah.
so when it's doing the maneuver, before it's doing the maneuver, there's a car over here, right?
sorry,
is
in
that
front?
No, here. This is the car.
Right. Right.
Is this car taken into consideration?
Yes, all cars are taken into consideration, but that car is parked on the side of the road.
Oh,
So
it's not moving.
yeah, I mean, we're moving at about 35 miles an hour in this experiment, so everything is with respect. Well, yeah, it's ego-centered, so you can't really see what the other cars are
I'm
doing.
just saying that, is this car taken into the consideration when you're doing planning?
Yes, yes,
So this car could accelerate, right?
yes. Then that maneuver would not be valid. Yes.
So,
But it didn't,
but it didn't, yeah.
so we don't have to care.
No, but it could. So I'm just saying that if it's me, I won't do this maneuver. This is quite dangerous because this car could accelerate.
No.
Yeah, I mean, you see all cars around you. I mean, it depends on the perception system, right? Like we have a maximum of 10 cars we can deal with in the.
I know.
In
But I'm
that
just
case.
saying that is the possibility of this car accelerating get taken into the consideration of generating this trajectory.
No,
No.
because it's constant speed model. But remember it's replanned at 20 hertz. So if you start to take to the left and then the car accelerate and you find, okay, this left trajectory is no longer valid, it will start to go to the right.
I know, but there could be another way is that because this car is slow, right? You say it's parked.
Yeah.
Then we should slow down, give us some space. Right? Then we go until give us enough space.
Yeah,
and
yeah,
even the-
actually,
even it accelerates.
yes,
it
yes,
allows
here.
rush hour.
Actually, if you see here, the first parameter it picks is actually to decelerate. But we put the deceleration parameter to be very small because we want to see lateral behaviors as well.
So that is taken into consideration.
The what?
The possibility that the car could accelerate.
I mean,
On the other side.
the first instinct of the safety filter is gonna be to stop the car, right? This is what
I
you
mean,
described before, right? Where
that's the fail-safe maneuver, right? But if you are not in the fail-safe maneuver, you're just in the regular operating regime, then it has, let's say it has like a 2-dimensional grid where x-axis is acceleration, y-axis is how much you want to move laterally. Then you have a cost function associated with each point on the grid, right? Like, oh, does deceleration means more danger, or lateral maneuver means more danger, and you can have a cost function that prefers to decelerate or accelerate over lateral maneuver.
So do you think you have a future plan to take that situation into consideration? That you're at one planning stage, you're like it's not assumed to be like how the cars are.
That's a prediction problem.
Yeah, I don't.
A prediction problem, not a planning problem. Yeah. Because they're taking into consideration all other factors in the environment. So as long as the predictor tells you that the other cars are moving, they're gonna shape into that area. I think this
Yeah.
is just because of the predictor.
I think the problem you're describing is not quite relevant to this, right? Because like, if you want to compute reachability sets for every single other vehicle,
Yeah.
you should just stay home, right? Don't leave,
Yeah,
right? Like, you won't get any.
so okay, so if the predictor is telling you that this car it's accelerating,
Mhm.
would this be taken into consideration?
I mean, yeah, as he was saying, we have a constant speed prediction model. You can
What is constant speed?
assuming they go constant speed for the future 8 seconds.
Oh.
But you can have a second order model which says, okay, I take its current acceleration and take its constant speed, take its current speed and interpolate it forward. Assuming it's
Yeah.
accelerating at the same rate.
That's CTR8.
Okay, so 8 seconds. 8 seconds is very large.
Yes, but
It's good enough.
you replan 20 hertz.
Sure, I'm also gonna say this, even in the F-110 racing case, if you have no measurement noise, CTRV is good enough. If you have. No, I mean, I'm saying that your error rate on using CTRV is gonna be comparable to that of a fully trained, or better than a fully trained LSTM or physics constrained model,
So
if you don't have measurements.
So basically, you're saying that since we plan fast enough,
Since, no, yeah, basically, if you plan fast enough, it doesn't matter.
Everything is static.
okay, thank you.
But could you potentially do exactly the same planning for all the other actors in the environment?
I mean, we don't have their trajectory parameters, and they may not drive according to our trajectory parameters, right? Like,
Can you identify that parameter? From observations of people?
sure, yeah, probably
Something that's
doing a similarity like
Mm.
check or something.
But like it's, the one that you design should be very general. I mean,
Right.
Yeah, hopefully, but yeah, I mean, I think this is okay, but it's still, for example, it doesn't have like, oh, let me avoid this pothole and come back to the eagle lane. Yeah.
But it's still operating as a filter over something else.
Yeah. So the high level decision to change lane or not is decided by
To drive it.
no, by autonomous algorithm.
Okay.
So how is this related to control variable?
Not. We compare it to control barrier functions, and they're like the vanilla version operates at 1.5 second ish, right? Per planning step.
What?
Second.
Second.
And this operate at 20 hertz, right?
So you're saying CBFR like slower?
CBRFR is no. I'm not talking about vanilla version of RTD. RTD
Ah,
does every 1.5 second it chooses a new trajectory. Yeah. This chooses a new trajectory every 20 hertz. But I think CBF can choose trajectory much faster, right? Like
Yeah.
which is good.
Right.
How do you compare the
I forgot I didn't do that comparison. Yeah.
you can't do the slicing, for one.
For which one?
basically if like CBF is usually one dimensional, is that right? I don't remember. Like, can you do like a lateral at the same time as the longitudinal? Yeah.
What's multiple CBFs?
It's basically a function with a real value over the whole space.
But the problem is when you start having multiple constraints, then you have the feasibility problem. So that's why I was asking how you know that there is always a fail safe.
Yeah. So I think let me quickly talk about the feasibility problem. So since we plan at 20 hertz, but we don't want to like change our maneuver every second, then it's gonna be uncomfortable or seem unpredictable to others. So we basically have a state machine that holds our, if we decide to edit our reinforced learning action, we would hold it for some time in the future. And of course, if during the holding, this new one is no longer safe, then we choose something else. And one good thing about this is if it turns out to be none of the corrections are feasible, we can still choose one that is least safety violating, meaning we have each constraint's violation value basically, and we can say, okay, let me choose the one that hit the least. And I mean, it turns out sometimes it is actually useful for that. For example, this one here, like when you get here, did you see that it briefly flashed all yellow? It's when it's none of the trajectory is feasible. Actually, what happened? Yeah, about here. It's because I set the laying edge as a constraint as well. So it will say, okay, everything is gonna hit the laying edge. What am I gonna do now? It will try to avoid the laying edge as much as possible.
Where is the break hard? Where it's break hard. Because breaking hard seems to be a way of avoiding
Yeah.
Where is the limit from the deceleration?
Yeah, the deceleration limit is 1, is -1. So
you
we don't.
put like priorities among like the different.
Yes, there's a cost function, and there will be a different cost function when none of the things are available. None of the
Can you have some slack on some of the constraints? Like,
I mean,
for the lanes,
that would be the same as this, right? Like choose the least well, choose the least violating is sort of like a slack, but I guess it choose the least violating and choose the lowest cost one is sort of.
So your zone approach,
Yeah.
how do they deal with it? Because in my understanding of the zone approach is you're computing the whole reachable space and then to obtain like the correction factor. Are you solving like a optimization problem there? Like how are you?
Yeah, so
Because it's not just the closest one anymore, it's the one with the least cost, right? So it's like a slightly different formulation. I don't know how you do the search.
so I mean, we just prefer to go straight. So we don't consider it as a let's follow the high level deletion as much as possible anymore. We just say, okay, if the high level deletion is crap, let's throw it away and try to go straight, but do as much as we can to ensure safety.
Got it.
Yeah. So actually, that's these two work, and a third one is on the F1 car, F1 tenth car, which we get rid of the error reachable set by doing a feedback linearization controller on the vehicle. So the zone level generation module only sees a pretty linearized dynamics. Therefore, it can generate fully sliceable reachable set, not including error reachable set. So let me just skip everything and show you guys the result.
Is this out, this paper? Can we read it?
It's on archive.
You would have known if you come to one of the meetings that often percentage. Cause that was just him and me talking about the paper.
Yeah. Fair. Fair.
And we were able to run this in our lab.
Where is this, Pennovation?
This is Michigan.
Oh, okay, okay. Look, this looks nice.
Is this you throwing the bus?
No, it's one of the people on the team. One of the master students.
There's so much light in there. Can you see the sun?
You've
Yeah,
been to unlimited body slap, they all look like this.
yeah, we
It's
had
just the
one.
pen ones are super bad.
We
I think it's old. It's just
Yeah.
a little old.
we had
All the other ones are built new.
we had one in Connecticut. It's just floor to ceiling windows. The only thing interrupting it was the floor of the next floor.
Trade-offs.
Dude, I went outside yesterday and my eyes couldn't adjust to the idea that there was actually natural light.
So this is just dealing with static.
Yes, yes.
How hard is it to implement?
Very hard.
Very hard.
If I want to
Uh,
do this in C++, for example.
We did this in C++. It's probably out open source. We probably don't need to do it again.
But if, like, how long did it take you guys to do it?
I don't want to say it.
Months?
No, it's like about a year.
Wait, and how many people did you have doing?
3.
And
I think the
What
problem.
is the hard part?
So we first have to do the car modeling, and which takes a while. But I guess it's because we don't have too much car expertise. Our lab does a lot of things. Walking robots, drones. Nobody is like not the whole lab is expertise on a single platform, which is good and bad.
so, do you have a Vicon spaces?
We have a Vicon space. We don't use that here. It's
So when you did the model ID for the car,
we did SLAM. We did a VL. It's a Honoco LiDAR. Yeah, and actually the suspension was giving us a lot of problems. So we changed out the springs for we changed out the springs for very, very stiff ones. And then when you drive it, you actually feel like it's a race car now. It's not a buggy car anymore.
I think you can
I think
actually,
this is what you have them.
Yeah,
this is what we do with all of our.
you have to change this.
We just got the McMaster one that's kind of like 20 Newton per meter.
You can get ones for the tractors. Actually, what I did back, I didn't know that these existed. So what I did is I had 2 other car kits and they all have bags of spacers, right? You jam in spacers so that half of the distance is
Ah, right.
spacer,
Yeah,
and that spring gets really
stiff. Yeah. Nice.
I mean, optimally, you just 3D print something.
To like
To
a
just be a
spacer.
solid.
Yeah.
So what's the use of this extension?
It's really good for normal people.
For what?
Well,
Nothing.
for if you want a good
Oh,
model.
It's a.
If you wanna go- If you want to go off-road,
Off-road,
even if
yeah.
you want to race, like body roll is a good thing.
Oh, really?
Something.
Kind of, a little body roll. A little body roll is a good.
The
thing.
weight
The
shift.
other chassis you have, the suspensions are a lot smaller, so they have less travel, but you still need some travel.
Too much.
Too much vibration on it.
That's-
Yeah.
No, but it's good for tracking. Tracking on the surface.
Good for just in general, kind of need that.
So what's the next steps?
I'm not working on this anymore. I feel, it's too conservative to do very aggressive things.
So after having spending multiple years working on like safety-based RL, safety-based systems, your prognosis is not positive for it. Right, no, I mean, I'm like legitimately trying to understand this because
I don't want to say that. I feel like if you look at YouTube for Rom's presentation, he extended this to the manipulator side, which is much more useful for these tools because they can compute the reachable set online, because it's like the manipulator by itself is not super fast system. You can afford to do things online, and you can also, and it was also able to do things like, I'm gonna take into account, like you can generate not zonotopes not only for positions. You can only generate it for force. You can say, okay, this is the force I'm gonna estimate. So if I move along this direction and at the same time have this much tilt, my water bottle is not gonna fall. But if I like it stops really quickly, then it's just gonna fall.
So that's non-linear.
Never been. Before.
Yeah.
But in this maybe.
The last one is linear.
Basically, it's a tool to talk about uncertainty and bounds on
So
things,
the other thing is
which
that why don't you, prediction, why don't you predict zone topes?
Me?
Yeah. For the car.
I mean, I didn't know there was zone topes existed before today, so.
But it seems really a lot easier than what you were doing.
Yeah.
Just a center.
so yeah, there are polynomial zonotopes which you should look into, and they have much more interesting shapes and non-convex shapes you can represent.
Why is it called those? It's
Why is it called polytopes?
poly is more.
What's tope?
It's a shape,
Tope
right?
is a position, like a shape. Right?
So what's zona?
Yeah, what's the role? Yeah.
Then there you go.
You tell me what's the.
I don't.
What's that game called?
Not too sure.
I don't know.
Not too sure.
Really?
Yeah, I don't know.
You working with someone for so long, you
Greek.
didn't search why it is like
It is definitely great. Right.
Yeah, so this was my master's, which, yeah, I mean, first I was doing some HJB stuff. I don't know if you guys know, like it's also safety stuff. Hamilton, Jacobi, Bellman stuff. And then started working on this sort of things. Yeah.
My main concern in this work is that it gives the guarantees, it assumes bounds on the uncertainties,
Yes.
which is reasonable when you're only considering noise or uncertainties. But sometimes your own model is also uncertain. So what happens in that?
So doesn't this kind of deal with that because of the?
Yeah, I mean, this is the model uncertainty that we put in here. We make sure that this is basically bounded, which, yeah, in your case, yes, it is a assumption, which, I mean, when you're on ice, all things are out of the window, right? Yeah.
Yeah, exactly.
Yeah,
Exactly.
yeah. So probably some online estimation of these parameters would be good. But at the same time, the controller needs to change. So I'm not too sure if it's immediately applicable. Yeah.
So what are you planning working on with?
Yeah, so I think I'm now trying a little bit to do some human robot interaction stuff. Carrying a table with a human, that sort of stuff. That's very different estimation problem, which yeah, I'm not sure yet, but that's the thing I'm looking at right now. But for cars, I also think like, so I don't think walking robots is gonna be that useful in that case. I feel like something like a mechanism wheeled manipulator would be good, but also maybe a car manipulator case, which have some planning properties, like if you know, like differential flatness is shown on a manipulator car as well. So it's
The
it's
only
useful.
thing I'd caution with mechanical wheels is they're very slippy. You can't, if I push it, you'll go.
Oh,
It's hard for them to. The static configuration does not have any, like, if you turn it off,
Mm.
it's freely movable. right? It's like Omni wheels, Mangharam wheels, they're all the same.
Mm.
But they're not resistant to torques. So you can take a Mangharam wheel chassis, and you can shove it and it will go, right?
Mm.
Any direction.
Okay.
Um,
You mean when the wheels are not locked or are
no,
not-
so the Mangharam wheels are different because they have those the freely
small
rotating ones,
wheels?
right?
Yeah.
So those will move in certain directions.
Oh.
Yeah.
Hmm.
And the Omni wheels in the lateral direction will always move, right?
Yeah. I'm not doing
Omni
any
are
Omni.
bad.
Yeah.
Mangharam wheels still have that to a certain extent.
Mm.
But you can counteract it. If you have a good controller, you can apply enough torque in that direction to counteract it.
Oh, really?
Yeah.
It's it's holonomic, yes?
Yeah.
Okay, yeah.
That's the advantage.
Yeah.
When you talk about carrying a table with a human, but you're doing carrying table downstairs with a human.
I'm
Or
talking about
upstairs.
like just moving it together.
You gotta start somewhere, right?
Meaning inferring intentions and where we want to go and
Yeah.
based on the force and that sort of stuff.
That's one good thing for Mangharam wheels though, because it will be really responsive to the force. Like
I mean the force has its own sensors like on the hand of
oh,
the robot. On the hand of the robot, yeah. But yeah. So I'm open to also use something like F110s or even a huge version of this
Yeah.
for that kind of application. So if you guys have ideas.
So you're looking at human robot interaction in general.
Yes and no. I mean, let me stop this.